Fantastic workshops. Thank you for inviting. You're the only one here to thank. And then Silke, thank you for this exchange. I need to catch my flight, so that's why I'm talking at Silke's spot, and all these people came to see her, and I mean, I take advantage of it. All right, so Penjan asked me to talk about kagome system, and actually my initial plan was I prepared to talk about iron germanium, but with all these talks we had yesterday, I changed the talk, so I will have basically ask me questions about iron germanium at the end. So I will focus on 135 materials, and I think the discussion yesterday was, the central point was, is the C3 symmetry broken, and is the time reversal symmetry broken in these materials? And my answer to that is no. And I will explain why I think it's not. All right, so 135, the samples came from Santa Barbara, Steve Wilson's group. The actual work was done by Shangfei Wu, who was my postdoc and currently in Beijing. Now, there was a collaboration on this material with Binhai on DFT part, and then Turan Birol helped us to do the group theory, and that's, I believe that's the beyond undergraduate new part that I want to dwell on. So that is actually an interesting part in my opinion. And this is all given in a long paper, which is, it takes a long time to read. So if you read papers that long, you cannot read 250 papers annually, as we were told, but it contains many things. And the iron germanium is online, so it's another complicated material. I'm going to skip the introduction. Julia spoke about this. We also heard about this, and I'm coming here. So the history, how I got involved. Steve told me that maybe it's interesting to look on Raman in early days. I was skeptical, but we did, and very happy that we did. Then about 2 years ago, Penjan was visiting us at Rutgers giving seminar and told me, well, there's a binary material, a binary kagome system, so it will be very easy to study. Yes. So we fell in that trap. Okay. I'm going to skip that. That was discussed. It's transport. This material has a CDW transition around 100K. So this A could be cesium or other metals in that first column. And this temperature of CDW varies slightly. And then there are superconductors around 2 degrees or 2.5 degrees. And that was also discussed. Then there were various claims on broken time reversal symmetry. So this is a surface probe. It's an STM, has not been reproduced data. And this we heard yesterday in glory details. So let me tell what we know about this material from the point of view just general group theory and X-ray refinement. So this 135 has alternating layers. There's 2 layers of this graphite type net, and that SB2, we call it 2 because that's its position. There is another SB which is in the kagome net plane. So this is sandwiched between these two graphite nets. And then, of course, there is this metal cesium in the corners here. Now, this kagome layer, which is mainly vanadiums, organizes in, well, there are two basic motifs. There is a Star of David motif and this other motif, which is inverse Star of David. So you get from one to another by just changing the displacement on an opposite side. And then the layered structure organizes by combining basically this Star of David and inverse Star of David with different amplitudes. And you can get various systems which have actually different properties. And turns out that some metals like cesium creates this 2x2x4 CDW structure. Others create bilayer structure. And I think we understand why this happens as well. So I'll talk about that briefly. So for notations, the Brillouin zone, so this is the gamma point, this is A point, and then the important points here are this M point, L point, and this line connecting M to L. And the instability, the lattice instability really happens along this line. So this is where the phonons have imaginary frequency, at least some of them, from DFT calculation. Now, quite straightforward charge susceptibility calculation that Binghai did in his group showed that all these points M, U, L have a maximum in uniform susceptibility at these points, meaning that the system is kind of less stable around these points, and those are the points that a system wants to fall from. And it's interesting that you can see that the color is almost same on all these points. So basically, the entire plane here is in principle active for this 3Q folding. So these 3Q charge density waves have been studied for a long time. And niobium diselenide has this type of charge density wave, etc. So if this happens at M point, then of course there is no doubling of the unit along C direction. All the planes are the same. If the instability is at L point, then the periodicity doubles. So this layer and this layer are different. Then again, we repeat that. And if it happens along the line, let's say in the middle of that, we call it U1 point, then the unit cell quadruples in Z direction. In AB plane, it's a 2x2 structure, and that comes automatically from this 3Q folding. Now, these M points are 3 times degenerate, L points are 3 times degenerate, U points are actually 6 times degenerate because this plus U and U below here are not equivalent. There is no crystallographic vector that brings one out, so it has more degrees of freedom. And the real structure, it turns out, is a combination of these distortions with different amplitudes. And it can be constructive, can be destructive interference, but it's quite complicated. So we did refinement, X-ray refinement. And for example, vanadium atoms, which displacement for vanadium atoms are in-plane displacement, the amplitude of this displacement is changing sign, and this direction is along the z. So each point here is describes layers. And so if I normalize it to the biggest displacement, then this displacement in the next layer is going to be opposite sign. There are actually 3 with opposite sign, and then it's again. And you can decompose these data points easily in harmonics. And that basically shows that it's really a combination of 4 displacements. For cesium, the displacements are along C direction, they're out of plane. 2 really are not displaced, and those are displaced. Again, I can decompose it in harmonics that I show here. So X-ray refinement for cesium material shows nicely that we have 2 by 2 by 4 structure. Okay, so now the complicated stuff, complication comes. So this is now important. So what is the symmetry of the ground state of charge density wave? And that is a group theoretical question, and it has group theoretical answer, precise answer. And the answer is the following, that if I do this 3Q folding to the new gamma point, the new unit cell can be either gamma 1 plus or gamma 6 plus symmetry. So in conventional point group symmetries, that means it's either A1G or E2G. If it's A1G, then the only broken symmetry is translational symmetry, and no point group operators are broken. So the C3, C6, everything should stay intact. If, however, the ground state is this, and there are 2 possibilities. If this is the ground state, then this is also our order parameter, but it's a failed order parameter in that sense that its energy is somewhere above the ground state, and by means of optical pumping, or by applying strain, or by doing surface probes, or doing some other things, one can get to this state. And I'll show we can get to this state. But this is the, so one of them is ground state, another is excited state, and I will argue that for this material, A1G is the ground state, and there's no other possibilities. Now, if the symmetry is broken and it's E2G, then the symmetry of domain is going to be orthorhombic, and there are going to be 3 equivalent domains which are 120 degrees oriented apart. In some sense, similar to what Liang was showing. Okay, and that's a strict group theoretical answer. So now, if the order parameter is, if we're folding M1, so we have only this possibility. The order parameter is L1, then it has L2 minus is actually mode. We have this possibility, same as before. Technically speaking, if we are on this line in between, then there are 2 other representations, and those break also inversion. We can exclude that because we do not see in broken inversion. It's well, by doing Raman spectroscopy, it's easy to identify broken inversion because infrared active modes will leak in Raman spectra, and we don't see that. Okay, now, once we know that, we can write down free energy. And this free energy is interesting because it contains this non-usual 3 linear term. and I will develop that a little bit later. So this intermediate below the TCDW, then the kind of subdominant another order, what was noted as T star, can rise from this term. Depending on the sign of gamma, I can manage to make it. This is the data that we saw yesterday, and it, well, first of all, it shows that the charge susceptibility is large in full symmetric channel. This is A1G, which again, I will show Raman data saying that point group symmetries are not broken. This also confirms that. So there is a weak signal in a non-symmetric channel, and you would expect to have weak signal if there is another subdominant order parameter far away. So it contributes to susceptibility, but it's suppressed. All right. So this is the game of free energy. If there is above the transition, everything is symmetric, and then below, this is basically a cut of landscape. Details are discussed in this paper, but you can have a minima which is away from this U point that determines what symmetries are going to be broken at this T star point, but basically the lattice symmetries will still stay intact, and that's consistent with the susceptibility that we see. Okay, let me now show the Raman data. So we can do symmetrized analysis. The way it's done is we use polarized light, and we do 4 polarizations, and then we decompose the spectra according to the representations, and we know which mode comes with what symmetry. Excellent. That's the 15 point. Huh? Yeah. Okay. So there is a main mode. So above the transition, above the CDW, only this SB2 atoms are Raman active, and the A1G mode, and there is E2G mode, and this mode need to be looked from the edge of the sample, and I'm not going to talk about that today. So this is the main mode in A1G symmetry. This is the main mode in E2G symmetry, and when we cool the sample, so this high temperature, we cool below the CDW, we get many additional modes. And these additional modes are because the unit cell is larger. We folded that phonon dispersion bands, and we get at gamma point new modes. So now we can look on these modes. So this is above transition. There's 2 modes as expected. And then let me go a little bit faster. So this is what happens below transition. This is the kitchen really. We do the measurement in 4 polarization, and then we can decompose and get all the symmetries. This actually shows, this plot shows, no, not this one. This one shows measurement on 3 compounds, on cesium, rubidium, and potassium. And you can see that in, broadly speaking, physics is very similar, but details are different, and we discuss in that paper the difference of the data. Now, below the transition, there are full symmetric modes, and those are folded modes, and you can see these guys which look like doublets. And I think, I didn't get confirmation from Leonard, sent him an email, but I think what he was showing are these doublets. These doublets are full symmetric. They are not really doublets. They are just folded modes. If you have a phonon branch which has little dispersion after you fold it, you will see 2 modes, and they are weakly separated. But this doesn't indicate broken C3 symmetry. In order to see C3 symmetry broken, you expect this true 2-dimensional representation, E2G, split, and see this is the main mode, and those are these extra modes that appear below the transition. You should see doublets here. And we don't see the doublets here. And that is kind of very strong Raman evidence that C3 is intact. Now, if C3 is intact, then the ground state has A1G representation. It's one-dimensional representation. And I cannot see how one can compose anything that would break time reversal symmetry. If this would be the ground state, then it's a two-dimensional representation. At least there is a ways to play. You need to get some complex order parameter here to build something that allows you to break in broken time reversal symmetry. But because I believe this is the ground state, the conclusion is that C3 is intact and the time reversal cannot be broken in this material. Now, how much I have? A minute, two? Very briefly. So this is the two main modes which exist already above the transition, and you can see there's some renormalization of frequency, certainly the relaxation time. Modes get much sharper below the transition, and everything gets sharper below the transition, right? And that should affect also muon measurements, muon time relaxation measurements. You can see this phonon, for example, gets strongly sharp. But there is also other stuff that happens at transition lower than TC. So this turns on at TC. It's essentially, some of them are just amplitude modes of the order parameter. But then you can see there's a kink here in this at some lower temperature, which is this T star. And for the modes of this C2G representation, there's more anomalies clearly seen so this is the red line is the TCDW, and there is another line T star where something happens which basically most likely is rearrangement of these compositions of the displacement, which still preserve the symmetry, but the amplitudes come differently and the interference pattern is different. And that, again, can be described with this model, and we discussed that here. So the second transition has been seen in many experiments. Yesterday, we saw example of that as well. And again, in that paper, we already kind of predicted that this can happen and exist. Okay, so in the cesium compound, the order is 2, 2, 2, 4. The group theory teaches us that it can either be hexagonal or orthorhombic. We showed that the bulk ground state is hexagonal, and there is somewhere nearby another order parameter to which one can twist the system by strain, by impurities, by I don't know what, maybe surface states. And that is probably the origin of the main confusions. And I basically don't have time to talk about iron germanium, I think, right? I'm out? Okay, well, if somebody asks. Oh, you want me to? Okay, I can, all right. I can do it quickly. So this material, which is binary, and we expect it to be extremely simple, turned out to be complicated. So there is a meal temperature at 410. There is Hunting transition at 60K was known, and then discovered here CDW. And then Penjing suggested us to look for that, so we went to look for that. So what? I don't go. So in few strokes, I will say what we know. We know that below Tn, in that system, already below Tn, the C3 symmetry breaks. And we can see that from the fact that in this case, a mode that's supposed to be degenerate, now this the E2G mode in this system actually splits. It's a very small splitting because the distortion is extremely small, but it was suggested from DFT that this imaginary frequency here is lowest for A6 minus mode, and A6 minus mode is a double degenerate mode. We doubles the unit cell and has essentially the following pattern of displacement of the germanium and also iron atoms. So the iron and germanium atoms shift in plane in opposite directions, some of them, or in this plane and neighboring plane. And that presumably somehow modulates the exchange, creating well, spin pairs-like antiferromagnetic modulation. So in my view, the unit cell doubles. As a result, they are kind of weak singlets forming what's called antiferromagnetic phase is actually really dimerization, tangency spin gap. It's a very small spin gap. It's millivolt. That means that all these effects are tiny, but trackable, clearly trackable. Okay, so that's the group theory. And then I'll try to be short, but what I want to say is at that temperature of CDW, there's broken translational symmetry now in plane. So we get 2 by 2 by 2 structure. And we see that in the Fallon's picture. So this is the business between, so new modes appear here, you can see, below the CDW transition. But then, very, very surprisingly, by cooling below this T counting transition, all these extra things disappear. I have never seen these kind of things in Raman picture because you believe that the entropy is increasing on cooling, you break more symmetries. This looks like the symmetry here recovers. It recovers the phase that it was above it recovers the paramagnetic phase. And we dwelt on that group theoretically. And the game here, I mean, it's possible. And the game here is the following, that because the lattice displacements are very, very tiny, the free energy that lattice takes is small. And so the entropy increase due to this counting phase that forms here is larger than the entropy decrease due to recovering the symmetry. So I hope we don't violate the third law of thermodynamics by doing that. But it's quite unusual thing where in a spectra you see the modes that are appearing in, well, and then we did all those things to show that this is actually possible and it's unique thing. So this paper is in submission. So it's kind of unusual symmetry ascending below the counting transition. Yes, thank you.
So this kind of symmetry recovering transition is usually a first order transition, right? Which you see in the...
It's yes, it's it depends on the, there are many possibilities here. Where is this thing? I had it. It's you can see that there's many parameters in the game, and you can play with that, and it's basically again an interference between different order parameters, which could be constructive and destructive, depends on the signs of all these coefficients, and then you can get. I don't think you can really get a continuous transition, but yeah.
Right, but you still see the CDW peak below the spin-canyon transition, while the Raman.
Yeah.
So these two are inconsistent.
In what sense?
I mean, you see the Raman is suggesting that CDW disappear at low temperature. And
no, CDW stays. Okay. At low temperature, CDW remains. Spin counting plus, there is a plus sign here, CDW. So it remains, but what happens is that the C3 symmetry gets broken already here, and that one recovers over there. But the translation symmetry breaks, and that doesn't recover.
But I thought you're showing this Raman mode recovers or disappear.
You're right. So those modes require actually not just CDW, but they also require broken C3.
I see.
And once one of them recovers, the mode goes away.
Very nice talk. So I have a question. When you say this strain can induce, let's say, time reversal symmetry breaking, and that's what also Philip Moll also was trying to show it in the recent paper. So we actually have done strain experiments where we can apply homogeneous strain on the cesium compound, and we don't see additional enhancement of the magnetic signal, right? Whatever we see at the ambient strain, we see the same under strain. But what we see is when you go to the surface, the signal increases by a factor of 5.
All right.
I think what happens is maybe you need inhomogeneous strain rather than
yeah, I can't really say what is required to bring this state down, and then plain vanilla E to G by itself also not going to break symmetry. You need to have imaginary part there somehow between these two components. I don't know how to. I honestly don't know how to construct that. But what I do now, I need at least that to start constructing something. Just with that, there's nothing. But yes, surface can do things, and as we discussed before lunch, so when you get closer to surface, you see stronger signal, and that could suggest that there is a contribution from the surface.
Yeah. But you know, if every material grown with some intrinsic strain, there's also intrinsic, right? You know, it's very difficult to characterize samples and, you know, to avoid completely the strain, right? You know, that's
and I don't actually, maybe I said more than I meant. I don't know for sure that the strain by itself will do that, right? So strain, if you do have 3 domains, you probably can stabilize one domain by straining the sample.
Last question.
Follow-up question, actually. You may answer this question too. So when you have the distortion, actually, there is any modification for the character of the magnetic moments, like over the iron, meaning like become more itinerant over different atoms, or more atomic?
I know about this atomic displacement, but I don't know about the moments. Maybe Penjan can comment on that. Yeah, everything is very tiny. In you're asking germanium, right? Yeah. It's very extremely tiny effects. Yeah, and I think that's why the recovery is possible, because typically lattice is the king. Once you distort the lattice, that's it. You can't. Magnetic energy is much weaker, and here it's possible that the magnetic energy can compete. Magnetic free energy can compete with them. Lattice distortions.
Yeah,
yes.
You show the iron germanium. In the non-magnetic phase, there's the implant distortion. There's a figure somewhere.
So again, in above Tn,
Okay.
paramagnetic phase, there is nothing. So it's all fine. So below Tn, we claim that C3 is broken. Very weakly, but it's broken. And it's broken by this A6 minus displacement, which is kind of unusual way to break the symmetry. So you basically on
I need this
adjusting
figure.
layers, you shift atoms in opposite directions, and that probably modulates somehow the exchange J between the layers. And then if it modulates, if you get this smaller than that, or vice versa, then you get, then you can get a AF M phase. But they work together, right? So like
Yeah.
in spin pairs, you minimize the energy.